All right, so let's go ahead and get started. So last lecture, we wrapped up the first part of the course. The course has 4 parts. So the first part was about combinatorial optimization, so efficient algorithms for searching over discrete structures, so things like flows, cuts, paths, and so on. And so with today's lecture, we move into our second part, which is all about linear programming with an emphasis on applications and duality. So how many of you have heard, have seen at least a little bit about linear programming at some point in your life? Just curious. Okay, I'm not going to assume anything. Don't worry. It was just for calibration. So it's kind of confusing for computer scientists because this isn't programming in like computer programming. So this predates kind of basically modern computers. So it's more like in the spirit of television programming, which means you basically are scheduling things. You're sort of like planning out what's going to happen. So that's the idea of linear programming. Same reason in dynamic programming. Okay, so same notion of the word. So why are we going to spend 2 full weeks on this topic? Well, so first of all, linear programming is algorithmically really, really useful. Okay, both if you're trying to prove theorems and also if you're trying to solve problems in the real world. So linear programming, if you remember only one thing about it after 261, remember that it's a remarkable sweet spot between, on the one hand, generality. So in particular, every problem we've studied so far can be thought of as a special case of linear programming. And on the other hand, computational efficiency. Okay, linear programs can be solved fast, both in theory and in practice. So sometimes, and we'll see many examples, the problem you care about literally is a linear program. But there's also cases where even though your problem isn't a linear program, it's still a super useful subroutine to sort of have in your pocket. So we'll have some lectures toward the end of the course on approximation algorithms for NP-hard problems. So we're not going to solve an NP-hard problem exactly using linear programming unless P equals NP, but still a linear programming solution can serve as the basis from which we recover a near-optimal feasible solution. So we'll see that at the end of the course. And then in practice, we don't really discuss this in 261, but in practice, probably the most cycles are used for linear programming actually as a helper subroutine in what's called integer programming. So that's a harder problem. It's NP hard, and people work hard to solve it exactly in practice because often, the viability of their business is depending on having a sort of efficient allocation of resources. And so in those integer programming codes, they invoke linear programming over and over and over again as a subroutine, because that's really the workhorse of how those things get solved. So that's the first reason, is it's really sort of a very general but still computationally efficiently solvable problem. But there's a second reason, which is also going to be very useful for us, which is just on a conceptual level. It's really helpful, meaning it just gives you the right way to think about lots of problems. So like for max flow, I tried to explain how the right way to think about the problem is in terms of these optimality conditions. No ST path in the graph. How do you know when you're done? You know you're done when you've saturated a cut. We had a similar thing with matching. So linear programming duality can be thought of as a generalization of all of these things that we've learned. In some sense, it's one of the more general answers you could ever have to the question, how do you know when we're done? Okay, that's really what duality is all about. So we'll start talking about that next lecture. So needless to say, this general answer to how do you know when you're done, it's super useful for proving algorithms are correct or at least approximately correct, because it sort of gives you a bound on how good any solution could possibly be. All right, so what is linear programming? Well, one way to think about it. So once upon a time, maybe a long time ago for some of you, but in at least one previous course, you may have forgotten it, but I'm sure you've seen systems of linear equations. Which can be thought of as an easy special case of linear programming. All right, so what do I mean by a system of linear equations where you have variables, x1 up to xn, and then you have a linear combination of them. Okay, so that's one linear constraint. So here we're thinking of the a's and b's as given, and the x's as free variables that we're solving for. And it's not just one linear equation, it's a system. Okay, so in general, you're going to have m of these. And so if you prefer in matrix form, you might want to write this like so. So you have a matrix A, so the columns correspond to variables. So there's n columns. The rows correspond to constraints, so there's m of those. So this again is given. These are the coefficients, the little a's. This is what you're solving for, and you're also given a right-hand side, b, which has length m. Okay? So one number per constraint. All right? So if you like matrices, that might be how you prefer to think about this. So when you study this, I'm sure you learned a pretty good algorithm for solving a linear system, in the sense of an algorithm that either determines that there's no feasible solution at all, or if there is a solution, it returns one to you. Right? So like Gaussian elimination would be a canonical such algorithm. Okay? And this is the kind of thing, maybe some of you even learned it in high school, but certainly, by the time of the first year math sequence here, one learns this stuff. Okay? So what does this have to do with the problems we've been talking about? Well, and what's like a key problem with Gaussian elimination in linear systems? Well, what about inequalities? And if you think about the problems we've been studying so far, if we wanted to try to encode them in this sort of language, it seems hard to escape wanting inequalities. Think about maximum flow. Okay? What did our constraints look like in the maximum flow problem? Well, we had conservation constraints. Those are equations, so that's not a problem. But then we had capacity constraints. Right? The flow on an edge should be at most the capacity of the edge. It shouldn't necessarily be equal. It doesn't have to be equal. It can be less. And actually, we also had these non-negativity constraints. So the flow should be at least 0 everywhere. And it's hard to see how you would encode that into just a system of linear equations. Okay, it really seems like you capture more problems by adding inequalities to these systems. And again, just thinking about max flow, it's sort of obvious we might want to do that. Okay? All right. Right, so one way to think about linear programming is, well, Gaussian elimination and algorithms of its ilk, they check feasibility of a system of linear equations. Linear programming can be used to efficiently check the feasibility of a system of linear equations and inequalities. Okay? More generally, if you have a range of feasible solutions, like you have many flows in a network, linear programming will allow you to optimize over all of the feasible solutions. Okay? So that's the purpose of linear programming. All right, so we're going to have several lectures on linear programming, and we're going to do lots of examples. I basically want us all to spend some quality time with this idea, because it's one of those things where, like, if you just see it in one lecture, it just doesn't sink in. It's something you need to kind of spend some quality time with to really absorb and then actually use in your later studies and work. So what's the ingredients of an LP? So you can sort of think of linear programming as this formalism, this sort of almost, programming language for encoding certain types of problems. Okay, so let me tell you what are the ingredients, and it's very flexible. Okay, so it's a recipe, and as I'll try to convince you even today, it's a very flexible one. So basically, we have to specify a linear program, you have to say what's allowed, and you have to say what you want. Okay, so the first thing you need to decide on are your decision variables. These play exactly the same role as in x1 through xn that I just erased. Okay, so each of these is a real value, positive or negative. So these are just free parameters. So it's the job of a linear programming algorithm to figure out the best way to set values for the x's. Okay? All right. So then you have to discuss what's allowed, what's feasible. Okay? So there's going to be constraints, and no surprise, given that it's called linear programming, the constraints should be linear. Okay? So like the ones we had in a system of linear equations, except we're also going to allow inequalities. Okay? So these are going to have the form sum over aij. So a linear combination of the x's, the a's are the coefficients. That's going to be the left-hand side. Then we're going to have a bi on the right-hand side. And in this space, this can be equals, or it can be less than or equal to, or it can be greater than or equal to. All right? So all of those are allowed when you're defining a linear program. Okay? Now again, let me emphasize, when you think about a linear program, you think of the A's and B's as part of the input. Okay, so they were just known numbers. 7, -1, etc. The X's are the free variables that we're solving for. Now, you may sort of observe that, allowing these 3 different types, really this is a superfluous encoding, but it's convenient. Remember, I'm not assuming that the A's or B's are negative. Okay, or non-negative. They can be positive or negative, that's fine. So given inequality of this form, I can translate it into one of this form just by multiplying everything by -1. Okay? And similarly the other direction. Even equations, if you think about it, are sort of a redundant encoding, because if I want to say something is equal to 10, I can just have one inequality saying it's at least 10 and a second inequality saying it's at most 10. Okay? So really, without loss, you can think of it as all inequalities and all going the same direction. Okay? We don't per se, but it's easy to have a workaround, and one of today's examples will show you the workaround. Yeah. So when you input it to an LP solver, you're really sort of stuck with this language, but it's not a big deal, okay, as we'll see. Good question. Other questions? So again, AIJs and BIs are constants, meaning numbers provided as part of the input, okay? So for example, like an edge capacity, that's what I mean, right? That's just gonna be like 12 or whatever in some given input, okay? All right, and then you have to say what you want. So just like in the specific problems we've been talking about, we need to posit an objective function. And, so I should say, okay, more in a second. So this should also be a linear objective function. It can be a minimization or a maximization function, it really doesn't matter. And then you get to choose some other linear combination with different coefficients, CJs, and you want to maximize the sum of the CJ XJs summed over J. Okay. Now again, there's no assumption that the C's are non-negative, they can be positive or negative. So then it's sort of immediately clear that it really doesn't matter whether you write it min or max, right? Because if you have a max, you multiply it by -1, you may as well minimize that instead. Okay, so you can transform one objective into the other objective just by taking the minus times the coefficients. Okay. All right, and that's it. So you specify those things, you've specified a linear program. You can start talking about solving it and what it means when you solve it and so on. So, linear, what does linear mean here really? How should you think about it? Well, so maybe it's simpler to say like what would be a violation of these rules, of the linearity rules. Okay, so it's certainly not allowed is to have one of your decision variables, an x, embedded in some nonlinear function, right? So like if log 1 plus x showed up, that would be nonlinear because log is not a linear function, okay? Similarly, if you had x1 squared, that would not be linear in x, right? That's a quadratic function, not a linear function. Also, if you took like two different variables, xi and xj, and multiplied them together, again, that would not be linear, okay? It would be a quadratic term, just with two different variables. So what's special about linear inequalities and linear objective functions is that whenever you see a decision variable, whenever you see an x, it's just alone, except possibly multiplied times some constant. And again, remember, the a's, b's, and c's are constants provided as part of the input, okay? And then, of course, you can sum them. That's fine for a linear function, all right? Okay, so so if you want to just check is something linear, is it not linear, just look at the decision variables, make sure they all appear by themselves, multiplied by constants, and then added up, and nothing else, okay? In particular, no products. Okay. So, the restriction to linearity, it's admittedly, significant. There's problems we care about which are not fundamentally linear. But still, as we'll see, there's a ton of applications, that are exactly modeled or approximated by linear programs. Sometimes the translation's super direct, and we'll see an example of that when we go to max flow and min cost flow. But I'll also give you a couple examples today motivated by machine learning where you need a couple tricks to really get the linear programming formulation. Okay? So sometimes you need some ingenuity, but I'll teach you some of the tricks of the trade in these lectures. Okay? All right. So I do want to do one toy example. All of our other examples will be actually quite real examples. So this is the only sort of simple toy example. Why am I doing it? Reason one is just, to make all this stuff a little less abstract, so you're sort of sure what we're talking about. But secondly, because I want to develop some of your geometric intuition about what it means to solve a linear program. And of course, it's much easier to have geometric intuition when you have 2 or 3 variables, you're in 2 or 3 dimensions, than if you have, 100 dimensions. Okay, so consider the following linear program. So there's going to be just 2 decision variables, okay, x1 and x2. We want to maximize their sum, okay? That's the objective. So I have to tell you about their constraints. So let's say that I'm going to require both to be non-negative. Those are 2 of the constraints. And then I'll posit an upper bound on 2 specific linear combinations. So that's evidently a linear program, 2 variables, 4 constraints, okay? So among everything, so what is it asking us to do? Among everything that satisfies all 4 of these inequalities, find the one with the biggest sum. So what would that look like in a picture? Since there's only 2 dimensions, we can think about candidate solutions as points in the plane, okay? With their x1 and x2 coordinates. So first, before we worry about what's optimal, let's just worry about what points actually satisfy all 4 of these inequalities. Well, let's just go through the inequalities one by one. So first of all, the first 2 inequalities say we basically are only looking in the non-negative quadrant, right, the northeastern quadrant. So wanting x1 to be greater than 0 says we should be on the right-hand side of this line of the y-axis. And saying that x2 should be non-negative says we should be north of the equator, okay, so above the x-axis. So how about these 2 constraints? So let's start with this one. So it's probably simplest to just say, okay, where does the line defining this inequality hit the axes? Okay, so for what values of x1 and x2 do we have 2x1 plus x2 equal to 1? Okay. So that's a line, right? The solutions to 2x1 plus x2 equal 1. So we sort of think it might hit this 0 1 or 2 times. And it hits it twice, right? So if you take x1 to be 0 and x2 to be 1, this constraint is satisfied with equality. On the other hand, if you take x1 to be a half and x2 to be 0, it's also satisfied with equality on this axis. And so the entire line segment between these will also satisfy that with equality. Right? So the set of solutions that satisfy an equation is just a line in the plane. Right? So symmetrically, right, and so what does the constraint say? It says you have to be southwest of this line. Right? So 2x1 plus x2 should only be less than 1. Okay? So this is 2x1 plus x2 at most 1. And then symmetrically, you've got this. Okay. This is not really drawn very well to scale. In your mind, think of this as symmetric. Okay. So what's the feasible region? Well, it's points that satisfy every single one of these inequalities. So it has to be in every single one of the 4 half planes that we mentioned. It has to be above here, to the right of here, below here, and below there. Okay? So that's going to be this parallelogram, or this trapezoid. So this is called this feasible region. Okay? So the feasible region is the set of all ways to set the decision variables so that all the inequality constraints are satisfied. Okay? Possibly with equality, possibly not with equality, possibly with slack. So any questions about that? Everyone see that that's the feasible region? Okay. So how about optimizing over the feasible region? Right, so we're supposed to maximize the sum. So a good way to think about that geometrically is, if you think about it, so that's saying we want to go in the direction of the vector 1, 1 as far as possible. I.e., we just want to go northeast as far as we can. Okay? So what can we imagine doing? Well, think about the level sets of this objective function. Okay? So it's a level set. Remember, so if you fix a value for a function, the level set is just all of the inputs to the function that give you that value. Okay? So you might want to know, what are all the pairs of points? If I feed it into this function, I get the value 10. Okay? And usually I have to erase what the previous class did in this room, which I think is some linear algebra section. But I fortunately noticed, before I erased it, that up there actually are the level sets of a linear function. Okay? So they're just these parallel lines. Okay? So one line for each possible value that the function can take on. Okay? The lines go orthogonal, perpendicular to the direction of the objective. Okay? So if the objective is going straight northeast, the level sets go straight from northwest to southeast at a perpendicular angle. Okay? Because all of those have dot product 0 with the objective function, so they all have the same objective function. Okay? Whatever it may be. So in this picture, the level sets for this objective function are just 45-degree lines, parallel. Okay? And as we look at higher and higher function values, we're looking at level sets that are further and further northeast. So in saying that we want the point of the feasible region with the biggest objective function value x1 plus x2, what we're saying is we want the feasible point which is on the furthest out level set. So just imagine in your mind that you do kind of a sweep line algorithm. Okay? So you start a 45-degree line way down here. You just move it to the right. At some point you're going to hit the feasible region. You're going to be passing through the feasible region. And then just at the point that you're about to have no intersection at all again with the feasible region, you pause, you stop. Okay? So this is like the last level set. In this case, the most northeastern level set that intersects the feasible region. That's going to be your optimal point. Right? So in this case, the most northeastern point, the one on the final level set, is this corner here. Okay? So this is the point 1/3, 1/3 for an objective function value of 2/3. Okay? So any questions about that? Clear? Okay. Say goodbye to the level sets then. But keep them in your mind. All right. So this was just a toy example, and you may be wondering, is any of this geometric intuition an artifact of us being in 2 dimensions? The fact that we can draw it is an artifact of being in 2 dimensions, but actually all the intuition we just developed is not. All the intuition we just developed is true for general linear programs. So the algebra remains the same, even when we can no longer visualize it once we have many variables. So in general, right, so notice the number of dimensions corresponds to the number of decision variables. So imagine you had a linear program with more like 1,000 decision variables, which is not at all unreasonable. Super high dimensional space, but it's still true that the feasible region, okay, it's not a polygon. Polygon is what you'd say in 2 dimensions, but it's the higher dimensional generalization of a polygon. Okay? So it's the intersection of half spaces. Okay? So one linear inequality is one half space. So the boundary of the half space is where this inequality holds with equality. So remember, when you have an equation, the solution set for a single equation is going to be a hyperplane in space, right? So if you're in Rn, you're going to have a hyperplane of dimension n minus 1. That's going to be the solutions of a particular equation. With an inequality, you just get everything on one side of the half plane, okay? Of the boundary. So you get a half space, okay? So one linear inequality gives you one half space. To be in the feasible region, you have to satisfy every single inequality. So you have to be in the intersection of all of these half spaces. Okay? So that's what feasible regions look like in general. In your mind, you might just want to think about like in 3D, a dodecahedron, something like that. But in general, this is true. Okay? Intersection of half spaces, just like that was the intersection of 4 different half planes. And so again, the level sets of the objective are just going to be parallel hyperplanes. The objective function will serve as the normal vector to these hyperplanes. Okay, so just like the picture I erased, you're just going to have these parallel hyperplanes. And again, let's say it's a maximization linear program. You just want to go as far as possible in the direction C. Okay, so you've got to be feasible. You've got to stay in this intersection of half spaces. And you want to go as far as possible in the direction C. So again, in your mind at least, this isn't how you'd code it up, but in your mind you can think about this sweep algorithm where you just start down at minus infinity and sweep this hyperplane perpendicular to the vector C and look at the last point that it touches the feasible region. That's going to be the optimal solution to the linear program. Okay? So I say farthest in the direction C, that's assuming you want to maximize. If you want to minimize, you want to go farthest in the direction minus C. Okay? So in some sense, I mean, thinking abstractly about a linear programming problem, it's actually very clean. It's a very simple problem. You just have the higher dimensional analog of a polygon, so known as a polyhedron, and you want to go as far as possible in some direction while staying within that polyhedron. Okay? That's literally it. That's geometrically exactly what a linear program is. Okay? So any questions about that? So another piece of intuition we get from the figure, which holds more generally, so notice where the optimal solution was. Okay? It wasn't somewhere in the middle of the feasible region. It wasn't even in the middle of an edge. Okay? It was at one of the corners of the polygon. Okay? So confusingly, these corners, they're called vertices, which conflicts obviously with the graph terminology, but so be it. So generally a vertex, so generally opt equals a vertex or corner of the feasible region. Okay? So the last point at which the level set's going to intersect the feasible region, it might be a point. Maybe if it's just lined up exactly so, maybe it meets an edge, but then all points on that edge are going to be optimal. So in particular, the endpoints are optimal, and so on. Okay? So I'm not going to prove this formally. It's actually a little bit annoying, but it's correct. Okay? And the geometric intuition, I hope, is a proof of plausibility that this is what's happening. All right? So you have this n-dimensional object, has lots of corners. Again, you can think about a dodecahedron, but it gets much worse in higher dimensions. But at least you know that one of those corners is the optimal solution. Okay, the corner which is furthest in the direction that you want to optimize in. Okay? So there are some edge cases, which I don't want to dwell on, but I want to point out that they exist. Both these edge cases can happen, and linear programming algorithms are coded up to deal with both of these edge cases. So the first problem could be there's no feasible solutions at all. And if this is if you feed into an LP algorithm something that's infeasible, you want it to tell you it's infeasible correctly, right? That's sort of the goal for the algorithm. So like in this example, if I added an extra constraint saying that x1 plus x2 has to be at least 1, then there'd be no feasible solutions, right? Because the maximum value of x1 plus x2 we computed as 2/3. Right? So that'd be an example of an infeasible linear program. It can certainly happen. The other thing which can happen is that the optimal value can be unbounded. So plus infinity if you're maximizing, or minus infinity if you're minimizing. Now, hopefully it's clear that a necessary condition for this to happen is that your feasible region is unbounded. It has to have some direction where you can go forever, right? Because if it was bounded, well, then remember, you're just given these coefficients, this objective function, these C's. If it's bounded, every feasible point will have some bounded objective function value. So the only way this can happen is when you're dealing with a feasible region that's unbounded, and the converse doesn't hold. Just because it's unbounded doesn't necessarily mean it's going to be infinite, okay? So again, in this case, you want your LP algorithm to tell you that it's unbounded, and all of the existing algorithms will do that, okay? All right. So any questions about that? So I've spent the time so far just trying to get you to think in what I think of as a simultaneously helpful, simple, and accurate way to think about linear programs. Obviously, I haven't discussed at all, like, what does it mean to actually write a program for a computer to tell it to do like a sweep line algorithm or do something else. Okay, and I'm not going to say much about it. I'll say a little bit more on probably Thursday, okay? So what I'm not going to talk about right now is what do the algorithms for solving linear programs look like. Rather, what I want to do next is motivate why we care about those algorithms by showing you a bunch of applications. Okay? So if we can solve linear programming, then we can solve a bunch of other things that we care about. Okay? And then for now, just take it on faith. There are really good algorithms for linear programming. Okay. So applications, so things that reduce to linear programming. So honestly, you could teach easily a full course just on kind of famous and important applications of linear programming. I'm not going to do that, of course, but it's a very, zillions of things can be modeled as linear programs. So what I want to do is I want to do a couple examples which are quickly, just showing that problems we've studied in the past easily translate to linear programs, and then I want to work a little bit harder to show you how some basic problems in machine learning with some tricks also become linear programs. Okay? That's sort of the plan. Good. Right, so I guess just a historical comment. So linear programming, it was developed by George Danzig in '47. I'll tell you more about him later. And so '47 was right after World War II, so they were really motivated by military applications. So they were thinking about things like, how do you ship supplies from the factories to the troops as cheaply as possible? And if you think about it, like '47, that way predates computer science. So like the Stanford CS department was founded in '65, almost 20 years later, and we didn't have an undergrad major, I think, until the '80s. Okay? So this is way before computer science, even though they were really doing algorithms. But now, there really are a lot of sort of, quintessentially computer science examples which fall into the linear programming camp. So those are the ones I'm going to try to emphasize in class. Okay. So when I first said about motivating inequalities, I mentioned max flow. So let's return to max flow. Now, in fairness, max flow also predates computer science, but we're getting closer, mid-50s. So the claim is that, max flow, almost if you just look at the definition of the problem, it's immediately a linear program, okay? But let me just, make sure this is clear to everybody. So, we need to decide the decision variables and the constraints of the objective. So what are the decision variables if we want to have a linear program encoding max flow? One variable per what? Edge. Encoding what? The flow on the edge. Okay? That's what we're solving for, right? So that's what we want to know the answers to. Okay? So we have m decision variables, where m is the number of edges. Okay? All right, so constraints. Well, I'm sure you remember we had two types of constraints. We had conservation constraints. We had capacity constraints. Conservation constraints, what do they say? They say flow in equals flow out. Okay, great. How do you actually write that down in terms of these decision variables? Well, for all vertices other than the source and the sink, so remember delta minus, this is the notation for the edges sticking in. So this is going to be the flow going into V. So saying that it equals flow out just says that something over the edge is outgoing from V. I sum up those flows and I get the same number on both sides. Okay? So strictly speaking, to put it in the form that I told you about over here, what I should do is I should subtract this right-hand side from both sides and get a 0 here. So this will have the sum of some FEs and minus some sum of some other FEs equals 0. Okay? Observe that this is, in fact, a linear constraint. Right? Whenever a decision variable appears, it appears just by itself. Okay? And then they're just added up. So that's exactly what linear means. So these are equations. But then we also have our capacity constraints. And actually, there's one other set of constraints. Do you remember? Yeah, non-negative. So remember, in a linear program, a priori decision variables are allowed to be positive or negative. So if you want them to be non-negative, you got to explicitly put that into the linear program. Okay? So the number of constraints we have is n, or rather n minus 2, plus 2m. Okay? And really, by definition, by the definition of a flow, the feasible solutions to this system of equations and inequalities are the feasible flows in the corresponding network. Right? We really just define flows as the feasible solutions. And then for the objective function, well, I can literally just write down the exact same expression I wrote down for you when I first defined it for you. So it's the flow going out of the source we want to maximize. Okay? Again, that just was by definition our objective function for max flow. And staring at it, it's definitely linear. Right? It just sums up a bunch of FEs. Okay? So this was meant to be a really kind of easy translation. Agreed? Effortless to take max flow and make it a linear program. Okay. Now, we worked on these different graph problems, and sometimes we got lucky. We sort of changed the problem, but it reduced to one we already knew how to solve. But then sometimes something would just seem like harder, like we'd add costs, and that was a whole different dimension. Right? So we went from max flow. We talked a little bit about min cost flow on Thursday, and I mentioned how you need new optimality conditions. Right? You have to sort of redesign algorithms, which is true if you want sort of the absolute fastest problem-specific algorithms. But if you're taking a linear programming approach, I want you to notice it is totally trivial to just change this linear program so that it's suddenly the min cost flow problem. Okay? So the main thing is, well, okay, now edges also have costs. And so now you have a new objective function, which is minimize sum over the edges, the amount of flow on the edge times the cost per unit on the edge. Okay, this is exactly what I wrote down Thursday, as by definition the objective function value of min cost flow. Now, I have to do a tweak to the conservation constraints. So, because if you remember, I defined the problem in saying the feasible solution should push d units of flow from the source S to the sink T. So you'd also want to have at S, flow out equals d. And it would be redundant, but if you want, you can put at t, flow in equals d. And again, this is a linear constraint, just in the same way these are linear constraints. Okay? And that's it. Boom. All of a sudden, we have a linear program for min cost flow. So we didn't redesign anything. I'm envisioning a situation where we have a black box that solves linear programs. And again, in the real world, you do have black boxes that solve linear programs. Okay? So you figure out how to translate max flow. You're like, oh, actually I want costs. Trivial modification to the linear programming formulation. Okay? So that's giving you an initial sense of kind of how flexible these are and how powerful that flexibility can be. All right, so that was example 2. Min cost flow. So any questions about that? Everything clear so far? All right. Then let's move on to some examples that some of you may have seen related material if you've taken CS229, if you've taken some machine learning. But It'll both be problems we have not yet talked about in 261, and it'll also be at least slightly non-obvious uses of linear programming. Okay. So application 3, fitting a line to data. Okay. So you want to be thinking of some picture like this, where you have points. Precisely, what's the input? So you have m points, p1 up to pm. These are each lie in some dimension d. For this lecture, I'm totally fine with you always thinking about d equal to 1. That's already a quite interesting case. Okay? In general, though, a data point could have multiple features, as they're called, or dimensions. So, for example, maybe each data point corresponds to a third grader, and we have a tuple, like maybe a triple, saying, what's the income of their household, how many years of education do their parents have, and how many books do they have in their home. That would be associating a triple of numbers with each of these data points. Okay? So that would be d equal 3. In the picture, d equals 1. Okay, and then you're also given what are called labels. L1 up to Lm, and these are real numbers. Okay? This could be, for example, the test scores of this particular third grader when they're in third grade. Okay? Test score, I should say. It's one-dimensional. So in this picture, the way I've done it is think of these as just real numbers, d equals 1, and think of plotting them on the x-axis, and then think of plotting the corresponding label on the y-axis. Okay? Good. So what's the goal? Well, this is one of the most basic forms of what's called supervised learning. What does supervised learning mean? It means I give you labeled data. Okay, so the data are the P's, but I also tell you the answer in some sense, the ground truth, the L's, the labels. Okay? So what do you want to do? You want to, at least in this very simple example, try to understand the label as being a simple linear relationship of the point's features. Okay? So we want to compute a linear function, h, mapping basically P's to guesses for L, such that if I apply the linear function to xi, I get something that approximates, not xi, pi, I get something that approximates li. Okay? And pictorially, it's what you think. We're trying to understand as best we can a linear fit. So a linear explanation of the labels is a function of the features. Okay? So this isn't precise yet because this is a squiggle. I haven't told you what the squiggle means. But you see, at least at this level, what I want. So what are we solving for? We're solving for h. We're solving for this linear function. Okay? So again, let me make it clear. The P's are inputs. The L's are inputs. We're solving for h. Okay? So there's a couple of reasons you might want to do this. Right? So one, and this is what you hear more in a machine learning class, you want to do prediction. Okay? So maybe actually, given some new third grader who hasn't taken the test yet, you want to have a good guess about what they're going to score. Okay? So you learn about their features, you learn about all the relevant aspects, you feed it into your linear function h, and you interpret its output as a guess or a prediction for what the label of that point should be. Okay? So you train, meaning you solve for h on labeled data, and then you apply the results to unlabeled data you get later. In statistics, you may hear a story that's a little bit different, where you're more just doing data analysis or data correlation, or data exploration. So you just want to know, is there a simple linear relationship between what I'm observing, these test scores, say, and any of the features? Are they positively correlated, negatively correlated, by how much? So the coefficients of this linear function give you that kind of information. All right, so it's a very basic problem. How does linear programming help? let's be clear on the decision variables. Okay, I want to make sure everybody understands this. So we're solving for a linear function h. So linear functions are parameterized or characterized by their coefficients. So we're really solving for the coefficients in this linear function. So those coefficients are going to be our decision variables. So the coefficients a1 up to ad, and then also an intercept b, all real numbers of the linear function h of z, sum over j equal 1 to d, aj, zj plus b. Okay. So there's a bunch of equivalent ways to define linear functions. One of those ways is just functions of this form. Okay? So you take as input d numbers, d real numbers. You're allowed to take some linear combination of them, some fixed linear combination, and add something. Okay? So that's a linear function. Solving for the best linear function just means solving for these coefficients in the intercept. Okay? So there's d plus 1 decision variables. Is everyone clear on that? So again, the p's are given, fixed. L's are given, fixed. We're solving for h, that is, we're solving for the a's and b. Okay? All right, so let's specify what we want, right? So if all of these points were collinear, it's pretty clear what we do, right? We just return the line that goes through them all. Okay, but that never happens, okay? So you're looking for a line which does well. So how do we quantify that? Well, so first let me define the error of a particular line, a particular function h on a particular point. So error on point I. And geometrically, the error is just going to be the vertical distance between, so in this picture, it's going to be the vertical distance between the data point, comma, label plotted, and whatever line you picked. Okay? So the length of this is going to be an error on that point. All right? In general, it's sort of the difference between the actual label of one of these points and what your function predicts for it. Okay? So we're going to call this EI, and it's a function of the, depends on the linear functions, on the coefficients a and b. So what do? So we say, well, let's plug in the ith point, point pi, into the function defined by a and b and see what we get. So j equal 1 to d, aj, pij plus b. Right, so this by definition is the value of the linear function on this particular point, p super I. So this is our prediction, or this is this linear function's prediction of what's up with point I. But we actually know the ground truth for point I, right? We know its label. So from this, we want to subtract what we know to be the right answer. Okay? So that's going to be the error. Actually, we want absolute values here. Right? We want error to only be positive. Okay? So if you're too high, it's an error. If you're too low, it's an error. So we take the absolute value. Okay? Okay? So now the question is, so again, we're sort of striving for an objective here. So how do you combine the errors on different points into a single objective function? So we're going to do not the most common one, but still one which is interesting and used to some extent in practice. So you minimize over coefficients a and intercepts b, the sum of the errors. Okay. So that's how I'm going to define the problem of fitting the line for today. Some of you will have seen a different definition of an objective for this problem in the past. What would that be? Sure. So what? Yeah. I mean, you're saying the same. Yeah. Different ways of saying the same thing. So more common is to square these. Okay. Look at squared mean error. And so if you have squares, it's not linear. You can't use linear programming. It's actually still tractable by something called convex programming, which if there's time, I'll say a little bit about at the end of the course. So in addition to being able to solve this using linear programming, it's not actually a crazy objective to use. So one advantage this objective has over the least squares is it's more robust to outliers. Okay? So imagine that in this data set, actually because of a noisy sensor or something, you had an x way up here. Okay? Suppose I added this to the data set. That's going to drag the best line further up. And if you think about it, if you're minimizing sum of squared errors, then this point is going to be a much squeakier wheel with squared errors than under just normal errors. Okay? So this is going to dominate the computation, and so that's going to drag the line further toward the blue point with the squares than it would with this near linear function. Okay? So that's one reason you might care about this objective. For today, the main point is just it will help us further understand how to use linear programming. So no constraints. Okay? So I told you what the decision variables are. The coefficients intercept of the linear function. I told you the objective minimizes some of the errors. No constraints, right? A's and B's can be whatever they want. So are we done? Do we have a linear program? Is there anything nonlinear that I've written on the board? Good. So there is an aspect, so I mentioned one example which said you can't take a variable and take the log of it because that's not a linear function. But actually if you take the absolute value of a function, that's not a linear function of it either. Okay? So as stated, this is not currently something you can feed into a linear programming solver. However, it turns out absolute values are quite benign, and usually there's a simple trick which turns them into linear. So let me show you what that trick is. So issue not linear. So trick. So when you use the fact that the absolute value of a number is just the maximum of either x or minus x. It's one way you can think about the absolute value if you really want to. Okay? So what's the trick? We're going to add extra variables. Okay, so we'll still have a1 through ad, we'll still have b, but we're also going to have e1 through em, where m is the number of data points. What we're hoping is that this little ei will be equal to that absolute value, to that capital EI term. And the way that we enforce that that happens is by adding more constraints. So basically, we're going to have two constraints, one for each of the two possible cases that determine the absolute value. Okay? So let me just take the definition of capital E sub I, remove the absolute values. So it should be at least that. But keep in mind, this might be a negative number, right? So I add a second constraint, which just says it's also equal to minus of exactly the same number. Okay? So if this is 5, this is going to be minus 5. Okay? And the claim then, oh yeah, so what's the new objective? Well, so the objective is the same as it was before, except that objective wasn't linear because it had absolute values, but with the objective sum of the EIs, this is a linear objective, right? Because it's just a sum of a bunch of decision variables. And if you look at these constraints, these are also linear constraints, okay? Don't forget, so E is a variable, A is a variable, P is fixed, part of the input, B is a variable, L is fixed, part of the input. Okay? But importantly, you never see two decision variables multiplied against each other. That's why it's still linear. Okay? All right, so that gives us a linear program, and the key point is that at an optimal solution of this linear program, it's going to be the case that the decision variable e sub I is equal to exactly what we want it to be equal to, namely the error. Okay. So why is that true? So suppose the error is like 5. Okay? Then we're going to have two constraints, one which says it's at least 5 and one which says it's at least minus 5. So EI certainly can't be strictly less than 5, right? Because one of the constraints literally says it has to be at least 5. So by feasibility, EI can only be bigger than what we want it to be, bigger than the absolute value of what's in the upper right. There are feasible points where EI is strictly bigger than what's on the upper right corner, but those wouldn't be optimal points, right? So for some reason, these constraints read 5 and minus 5, and you looked at a feasible solution where EI was equal to 6, well, I'll show you a better solution where I just round EI down from 6 to 5. Okay? So that'll give me a smaller, I should say minimize. So that'll give me a smaller objective function value, a better solution. Okay? So by feasibility, it can only be bigger than what we want it to be, and by optimality, it's going to be equal to what we want it to be, equal to the error. Okay? Good. So any questions about that? So how would you fit a line under this metric? You'd literally just write down this linear program. It has m plus d plus 1 decision variables, and it has 2m constraints. You'd feed that in. You could ignore the EIs if you want, but the A's and the B's would give you the coefficients for the best linear fit under this particular notion of fit. Questions? Everything clear? Okay. So last application. Again, drawn from machine learning, sort of a very basic problem from that domain. Trying to figure out a good linear classifier. These are also called half spaces. These are also called perceptrons. Okay. So basically, the problem is very similar to fitting the line with the following difference. In the previous example, we wanted to predict a real valued quantity, okay, like the test score of a student. Here, the assumption is we just want to predict a binary object, okay, like given an image, is it of a cat or is it not of a cat? And that's it, okay? So the picture you might want to have in mind here. So this is now with d equal 2. So you're given a bunch of points. Some of them are labeled positive examples, i.e. they are cats. And some are negative examples, they're not cats. And you want to find a linear separator. Okay, so you want to draw a hyperplane so that all of the positive examples are on one side, all of the negative examples are on the other side. Okay? And again, if you could do this, if you can find such a hyperplane, how do you use this later for prediction of unlabeled data? Given some arbitrary image, you just check which side of the hyperplane does it lie on, and then you answer cat or not cat as appropriate. Okay. All right, so a little more formally. So the input, you have m positive points. P1 to PM, those are the cats. M prime negative points. The non-cats. One way to think about this, so before we had these labels, so we still have labels, now the labels are either just like positive or negative. And I've just partitioned the points for your convenience into the positive subset and the negative subset. Okay? So we still have the labels, they're just very simple labels now. Goal, compute a linear function, just like before, h of z equal to sum, j equal 1 to d, aj, zj plus b, such that, as we said, all positive examples are on one side, all negative examples are on the other side. So such that 1, hpi greater than 0 for all the positive examples, and 2, h of qi is less than 0 for all negative examples. Okay? So again, the p's and q's are given, and what we're solving for is h. And we're again thinking of h as being defined by its coefficients, a1 through ad, and its intercept, b. So the way I've written this, it seems, and so for now, no objective function, okay? Just a feasibility question. All right? Does there or does there not exist such a linear function? And staring at it, I mean, it feels like it looks really, really close to a linear program already, right? Again, with decision variables a1 through ad and b. The only thing which is different from a linear program, and this relates to an earlier question, is that we have strict inequalities in our constraints. Okay, we're solving for a linear function so that it's strictly negative on the negative points and strictly positive on the positive points. Right? Strict inequalities aren't allowed in a linear program. But actually, it's very easy to sort of simulate strict inequalities with inequalities in a linear program. So how do you do that? So the trick is to add just one additional variable, right? So your additional variables were helpful before to model absolute values. We needed m of them then. Now we just need one extra variable, and that's going to be measuring how far away from 0 we are in each of the two cases. Okay? So it's going to look like maximize over delta, and the decision variables here are the a coefficients, the b intercept, and this delta. And so we're going to replace this by just saying it should be greater than or equal to delta. We're going to replace this by saying it should be less than or equal to minus delta. Okay? So subject to yeah. And notice that there exists a solution to the original problem if and only if there exists a solution here with a positive value of delta. Okay. So feasible in the original problem if and only if the optimal value here is positive. Okay. If you can find a feasible solution with a positive delta, then it actually says something stronger than strictly delta. It's actually strictly bigger than 0. It's at least as big as delta, with delta bigger than 0. Okay? So that's quite nice. We'll revisit this example later, but is everyone clear right now? So if you want to find one of these separating hyperplanes, or rather if you want to check whether or not there exists a separating hyperplane, it's really just a straightforward linear programming computation. Yeah? Okay. And I want to emphasize, this is really a super basic primitive in machine learning. Okay, so it's not at all a made-up example. It's a quite real example. So the last point I want to discuss, well, I guess second to last point I want to discuss, which again will sort of showcase the versatility of this language for writing down linear programs. I want to show you a couple other topics very related to this one. So, you know, if I tried to pass this off as a practical subroutine, you would be right to make the following complaint. You could say, you know, real data is never going to look like that. Maybe you're going to have more pluses in one side than minuses, and the reverse on the other side. But you're not just going to have like all these pluses hanging out over here and then totally segregated all these minuses over here. There's going to be some intermingling. If nothing else, just from noise in the data. Okay? And if there's no way, right, so imagine I just changed, so imagine you had a corrupted data point, and this actually was recorded as a plus. This is a data entry error, okay? So now there is no hyperplane, which puts all the pluses on one side and the minuses on the other. You can solve this LP, and it's just going to go back and tell you, oh yeah, it's infeasible. There isn't a hyperplane, okay? But you kind of want to say, okay, but you know, I still think it's like mostly separable. Give me a hyperplane to use for prediction tomorrow, right? So how do you do that? So how do you overcome, how do you look at the more general case where there need not be a perfect separator? So question, what if no perfect classifier? Okay. All right. And so what I want to do is I want to show you how two other concepts in machine learning, which are sort of like have been big buzzwords over the years. You know, I just want to convince you that really it's just some more linear programming tweaks. Right? So you really kind of already know what's going on, you know, including with the basics of like support vector machines, if you've ever heard of that. Don't worry if you haven't heard of that. Okay, so let's look at two possible answers for this. So what do you do if there's no perfect classifier? Well, so I think the first and more obvious thing to do is the same thing we were doing when we were fitting our line, right? So remember when we fit a line to real values, we were assuming they weren't all collinear, so there was no perfect line. So we just looked at the error that a line made on each point, and then we sort of summed up the errors. So we try to do the same thing here, okay? So minimize error. So here we have to be a little careful how we want to define error. I think the most obvious way to define error would just say, you know, find the half space which misclassifies as few of the data points as possible. Okay, that's actually a hard problem, both theoretically and in practice. So rather, people use different notions of error, which you can actually optimize over. So I'm going to show you one very commonly used notion of error, which admits a linear programming solution. Okay, it's something called hinge loss. So here's the idea. So in our minds, we have the following like dream. Okay, we're hoping that the data has the property, ideal, that there exists an H such that, let's say, all right, we said strictly positive, but let's say maybe even like at least one for all the positive points, and at most -1 for all the negative points. So this would say actually something stronger. So in a picture like this, so to satisfy these constraints in a picture like this, it would have to be the case that each of these points not only is on the correct side, but actually their vertical distance from the boundary should be at least 1. Okay, so there should be a big distance between every minus in the boundary and also a big distance vertically between every plus in the boundary. So this is called having a large margin in machine learning terminology. Okay? So geometrically, that's what these constraints correspond to. Not only do you want to separate the points, but you want them to be at least 1 unit vertically away from the boundary. Now this choice of 1 - 1 is a bit arbitrary, but I have to fix some constant just to get a normalization. So I'm going to fix 1 and -1. Okay. All right, so let me define hinge loss. So on a positive point, All right, so I really want your classifier to put this vertical distance 1 or higher above the hyperplane. So what I'm going to do is, if you put this point less than 1 above the hyperplane, if you only put it 0.8 above the hyperplane, I'm going to penalize you for the difference. So I'll penalize you 0.2 if this plus point is only 0.8 above the hyperplane. If it's only 0.3 above the hyperplane, I'll penalize you 0.7. If it's below the hyperplane, I'll penalize you accordingly. So if it's 1 below the hyperplane, I'll penalize you 2. Okay? So that's the hinge loss. Basically, it says for every point, you say, okay, how far would I have to move this so that it's where I want it to be, namely vertical distance at least 1 away from the hyperplane on the correct side. So how do you write that in math? So this is just this. Right, so as h drops below, so loss is bad. Okay, so higher loss is worse. So as this drops below 1, remember you're hoping this is 1 or more. As this drops below 1, your hinge loss on this point goes up and up and up. Okay? So actually there's a detail. It's also not a good idea to just reward the classifier for putting points way on the correct side of the boundary. Okay, so you're not going to get a free 100 points just because there's this one outlier that, is way on the correct side. Okay, that tends to not work so well. So we're going to take the max of this with 0. Okay? That'll ensure, in particular, that the loss is always non-negative. Okay? So that's for a positive point. And then on a negative point, you're just going to do the same thing, except you're going to flip this around. Okay? So is it clear? So what I've defined is, I said fix a linear function. That is, fix choices for the coefficients a1 through ad and the intercept b. That defines an h. So we can now talk about, which corresponds to choosing a line geometrically. So we can now talk about, for a fixed line, we can talk about the hinge loss of that line with respect to each of the points. Yeah? Which?
Measuring the difference between HQI and -1.
Yeah. So as soon as this is, I see. Yes, you're right. So the point is you want to be incurring loss as soon as this is any larger than -1. So when this is -1, this will be 0. That's good. But then as it becomes bigger, closer to 0, you're going to be picking up a loss. Thank you for the correction. Good. Any other questions? All right. So the claim is that minimizing hinge loss is just an LP, or can be encoded as an LP. Okay. And this just is, if you follow the examples so far, you should sort of see how this goes. Okay, so your first attempt would be to say, okay, what are the decision variables? Same as before, A1 through AD plus B. What are the constraints? No constraints. What's the objective? Minimize the sum of these things. Okay? What's the problem? The problem is this is not a linear program. Why is it not a linear program? It's because in the objective function, we have these maxes. Okay? And that's a nonlinear operator. Okay? But we had this same problem earlier when we were talking about fitting a line, when our objective function had absolute values in them. And remember, an absolute value is really just a max between x and minus x. What was the trick? We added one extra variable for each term of the objective function, and a pair of corresponding constraints saying it's at least something and at least minus something. And that exact same thing works here. The only difference is your two constraints, instead of saying at least something and at least minus something, one constraint says EI should be at least this. The other constraint says EI should be non-negative. For positive points, for negative points, one constraint saying EI is at least this, one constraint saying EI non-negative. Otherwise, it's exactly the same as the fitting the line example. Questions about that? Okay. So if not, I have one last trick I wanted to show you. So this is so we asked the question, what do you do if there's no perfect classifier? We agree that if there is a perfect classifier, we're done. We just solve an LP and we find it. What do we do if there isn't one? Well, so one idea, I think the easier idea was to minimize error instead, except that you're going to misclassify some stuff. Here's a more sophisticated answer. And I'm just going to show you the tip of the iceberg, but basically what I'm showing you is sort of the initial idea of what's called SVMs, or support vector machines, which if you take CS229, you'll hear a lot more about. So idea number 2 is to not restrict ourselves to lines, okay? Allow nonlinear boundaries. So like imagine your cats and non-cats sort of look like this, pluses and minuses. And you observe that, well, you can't quite get a linear separator, but you can sort of get a pretty simple separator, perfect separator between the pluses and minuses, one that looks sort of like a quadratic curve. So that motivates the idea of having nonlinear classifiers. But then, I mean, clearly we were getting an enormous advantage from the linear classifiers of computational tractability. So how can we have sort of a richer set of classifiers without giving up on the ability to use linear programming, on the ability to actually solve for it efficiently? So here's the way we do it, is we just take the original data points and we add extra features, okay? And so what do? You take what was originally a D vector, okay? So this is like, the household income and so on, and, or, pixel values, and you map this to a D prime vector, where D prime is bigger than D, possibly much bigger than D, okay? So you enrich the feature set, and you may say, well, how do you do that? I mean, doesn't that seem like a very domain-dependent thing? To some extent, yes, but there's some tricks of just automatically blowing up the feature set, which in particular allow you to fit quadratic curves and that kind of thing. So what I want you to have in mind is think of, so if I feed in a D tuple to phi, think of what it gives me back. So it gives me back the original D features. Right, so I fed in Z1 through ZD. I get back Z1 through ZD. But then I get extra features, which are just the Z1 through ZD squareds, and all the cross products of the different features. Okay? And again, I encourage you to think about the D equal 1 case, where this is already interesting. When D equals 1, it just says phi of z is zz squared, okay? So we kind of artificially inflated the dimension of each of the data points. And now the idea is just to use exactly the same linear program we had before for finding a separating hyperplane, but instead of solving for a linear function to find in d-dimensional space the original features, we're going to solve a linear program in d prime dimensions using this augmented set of features. But again, we're just going to be solving for coefficients, so it's just going to be a linear program, albeit with higher dimension. So now the goal is compute A1 up to AD prime. Okay, so we're working in this higher dimensional space, plus an intercept such that, same thing as before. So for all positive points, so I sum over all of the D prime coordinates. So now instead of talking about the original point P, I talk about the sort of inflated version of P on the bigger feature set. So I write this like this. Okay, so it's a linear combination with coefficients aj on the vector of enriched features. Add in the intercept, I want this to be bigger than 0 for all the positive examples. And then I want the same thing to be less than 0 for all negative examples. Okay? So a couple comments to help you kind of start to understand what's happening here. So by enriching, so if we have a new feature set which includes all of the old features, so like here, we started with Z1 through ZD. We have Z1 through ZD plus a bunch of other stuff. You certainly don't lose anything. For any linear function of the original features, for any hyperplane you might have tried with the original point set, you're certainly welcome to try exactly that same hyperplane now, just by using a coefficient of 0 on all of the extra features. Okay? So the point being is we've only enriched the set of things you can separate the points with. Now how does this connect back to talking about quadratic curves? So again, think about the special case where we just have one dimension. So we map a point z to zz squared. Okay? So there's two features, sort of one corresponding to the original value and a second coordinate that's for the quadratic coordinate. Imagine you now, so now you're just computing two coefficients, an a1 and a2. Imagine you set, a1 to 0 and a2 to 1. Now all of a sudden your sort of new function h is z squared plus some intercept b. Okay? So by enriching the feature set and plugging in nonlinear terms explicitly into the features, you can actually still solve for a richer separating hyperplane. Not really a hyperplane, a richer curve. And again, the thing to remember, what makes this work, p was fixed all along. P is part of the input, so you can do any kind of pre-processing on p, and there's no way you're going to screw up linearity. You're just changing some constants into other constants. Okay. Anyways, now that we have this formalism, we can basically just pretend like these were our original data points. Right? So we did pre-processing, we blew up the number of dimensions, and now we just have an instance of our previous separating hyperplane problem, which we observed was just a linear program. And again, the one caveat is that the dimensions has gone up. It used to be d plus 1, now it's d prime plus 1, where d prime is possibly bigger than before. So like here, the dimensions blows up by a quadratic amount. Okay? Now for proper support vector machines, there's sort of an extra trick which allows you to do the computations as efficiently as if you were working in the original space. But that's something you should really take 229 to learn more about. So next time, we'll start talking about algorithms and also about duality. See you then.